All right, our next speaker chose in his first trip to the United States of America to come to Ann Arbor, Michigan. Youssef Nader is from Egypt and is a current PhD student at a university in Germany, and he is also a grand prize winner from the Vesuvius Challenge Phase 1. And Youssef is going to talk to us about his current work in ink detection and machine learning. Youssef.
Yeah, thank you, Brent. Yeah, hello everyone. Excited to be here with you today and to have finally made it to the US. So, picking up from Mami's talk, the ink detection in 3D is basically you have a 3D image. This the volume or the fragment that you're working with after it's flattened, and then the depth of, it's very high resolution, so we're so zoomed in on that. And the models are basically taking these small cubes, cutouts, and when you move these cubes all over the fragments, you get the prediction, which makes sense from a human perspective. This looks like Greek or Latin. And so before the challenge started, the first challenge that was run in the Vesuvius challenge was, how can we improve on these neural networks, and how can we sort of improve you saw how the images were very noisy, and you're barely making out the letters, but there is something there. So the first part of the Vesuvius challenge, which got me hooked, and I think it also got Julian hooked, was how can we do better than these current models? And contestants, they went all over the place, looking at the literature, like what different ideas could work for this. And they tried many different models. However, unfortunately, even though they managed to improve this noise ratio a lot, the signal on the unopened scroll remained just completely blank. We couldn't see anything, and that was sort of the area from which I started picking up the Vesuvius challenge. So you can treat this detecting ink as this sort of multiple output classification problem, which is the sort of the paradigm that emerged after the Kaggle competition. What this really means is, instead of doing ink or no ink on just one spot, you can also do it on a couple different spots. And you know how you made it into a tile, so it's more spatial resolution. You can now have like a finer predictions on, there's ink here, but there's no ink here, and there's ink here, but there's no ink here, so that you get sort of the shape of the letter, and you can sort of also have more context of what is going on around you. And these models usually are composed of two different components. There's a part that tries to look at the images and try to figure out what is there. Like, okay, I'm seeing this pattern. I'm seeing, there are like some brightness difference. There's this and that. And there's another part that takes in this information and starts deciding where to put the ink. So if you see, for example, brightness here, then maybe there's ink here. But if the brightness here is not changed, then there's no ink here. So we had working models for fragments, but these models weren't able to go into the unopened scroll. And my idea was, is it possible to learn something from the unopened scroll, even though we don't see the ink? Is it possible to maybe learn some properties of these images, so that when we show the model the fragments, it sort of remembers, I've seen this before, and then starts mapping this ink back to the scroll. And this sort of didn't work, but it also didn't not work, and it was this very gray area. So the idea comes from self-supervised learning, and the idea of self-supervised learning is actually a very smart trick. Let's say, for example, that you have a bunch of images for cats and dogs, but let's say you don't want to tell the AI model that these are cats and dogs, and you want it to figure out what is there on its own. One visual property that we humans have is that, for example, if I show you an image of yourself upside down, you would still recognize that this is your image. Why? Because it's your hair, your ears, your face, and the AI models don't really have this property baked into them. This is something they need to learn. So a simple idea was, if you take one of these images and you flip it, for example, upside down, the ink should still be there. Like if there's ink, it should still be there. And the model should be able to learn that this sort of visual feature is now flipped, so it needs to learn about all of these different patterns that occur in the image. It's the same way that you understand what is a nose, so your nose flipped is still your nose. And this was the idea that you try to teach the AI model, that internally, in the numerical representation it has for these images, it should be the same. This is the same image that I'm showing you, but it just has some different alterations. I changed, for example, the contrast a little bit. I flipped the image or rotated it. And this seemed to push the model in an interesting direction. And after training that model just the conventional way and showing it the fragments, it started picking up some letters. It was still very noisy. It was still, very unclear. But there was like this pie that was very clear in there, and there seemed to be some structures that are going on the same line. There seemed to be like multiple lines, and that was sort of the first exciting step. However, many experiments didn't manage to improve on this so much. So from there, I thought, okay, what if I just take what I see, and I also train the model on whatever I think is letters there. And so I took this image and I made another ground truth. It wasn't really a ground truth because I'm not sure where the ink is, but it was sort of a first step towards a ground truth. And you will notice, for example, there is like a very interesting part in this, which is the epsilon, lambda, epsilon at the top. And I have no Greek knowledge whatsoever, and I was just drawing whatever shapes made sense, and maybe stuff that maybe I think I saw somewhere before. But I took this and I trained a new model on this, and to my surprise, this new model did a lot better. It was starting to see a lot more, and with some clever optimization that I'm going to talk about later, it actually disregarded my epsilon, lambda, epsilon. Like it was, you don't know what you're talking about. There is nothing here. And this was sort of a very important property to bake into the AI models, that they can sort of argue back, that they can, know where the ink is. And if I make mistakes, they don't make the same mistakes. And then when this happened, I thought, what are the chances that if I repeat this process again, it keeps getting better? And this was the essence of the first letter solution and then the grand prize solution, this idea of iterative labeling process where the model finds some letters. There still could be improvements, but you let the model sort of improve on its own. So the next time, I'm just guiding the model of, you seem to, for example, be putting some signal between lines. This is not correct. There is this sort of human guidance, but the model is sort of becoming a teacher after it learns what the ink is. And then it sort of passes the torch to the next model. The next model has better training data, so it has a better idea what ink is. And then it passes the torch to another model. And repeating this process is sort of what got the models there. So the important thing up here is, how do you prevent memorization? How do you prevent one model from just, okay, you want these letters, you want this epsilon, lambda, epsilon, I'll just give you what you want. So there were a couple tricks on how to allow the model to disagree and how to prevent the models from remembering these mistakes. So the first step was to use smaller models, sort of the polynomial equations that Mami was talking about. You can make them more compact so that the model can't really memorize everything. Like if you have less neurons in your brain, you're not able to fit as much information. The second property was error tolerance. And how do you balance the data? How do you, give it the right amount of ink and no ink data? And how do you generate like data variations? So this idea for allowing the model to sort of argue back comes from this method called label smoothing. And the idea is, when I'm making a label, I'm not entirely sure that this is correct. Sometimes, for example, if this circle or this maybe there's some part that is missed. And when the model is trained, it's going to be shown this area, and it's going to be shown that there is no ink here. So the model needs to be, not be penalized because I made a mistake in creating this label. And the idea is that instead of giving the models like very high probabilities that this is 100% ink and this is 0% ink, you can sort of get these probabilities closer together so that, you know, the model disagreeing with me is not just such a leap of faith that, you know, it will have to agree with me. So, for example, if I say, yeah, well, I'm 80% sure this is ink or 75% sure this is ink, the model can say, well, it doesn't really, it's like 40% more likely. And this property is actually allowed the model to improve over my labels a lot, where I make a mistake, the model can still disagree in that area and say, well, you missed a spot here and there's ink. Another idea was how do you show the model the right amount of ink and no ink data? So one of the main properties of neural networks is that they are lazy. So if, for example, you show them a very little amount of ink and a lot of blank space, it's gonna decide that, you know, probably if I say that everything, there's no ink, I'm not gonna be penalized so much. It's still gonna be fine. And if you show them so much ink, they might decide that everything is ink. You know, like, okay, you want ink everywhere? I'll put ink everywhere. And finding this balance sort of, in the end, I landed on this idea of you take a certain area around the letters that you see, and that area is small enough such that you don't go into other letters. So if, for example, you see the pi, but you don't see anything after it, you're sure enough this is usually the space around the letter. So that was like around 256 pixels around the letter. And this sort of gives you a nice balance between, you know, blank space and letters. Another very important property that you know, we went over many times during the challenge was how do you pick the right amount of context that the model sees at any given point? So if you give the model a very large context, you know, like a very large cutout or tile, 512 by 512, for example, it can see usually the complete letter. What this means is it can oftentimes do some inferences about what the letter should be. So maybe the signal is missing in some parts, but it knows that you usually deal in complete letters, so it's gonna find a way to bridge that gap and give you a complete letter. Making this area smaller and smaller may prevent this, but for example, a 256 by 256 cutout still sees enough context that it may be able to make out what letter. It doesn't see the letter, but it's still able to memorize things like the brush stroke, for example. You know, these labels were made over Photoshop, so they have a certain width. Maybe this is not the exact width that is on the papyrus, but since this is what you want, this is what the model will give you. So in the end, we settled on the 64 by 64 cutouts, which you can see they're very tiny on the scale of the letter. For the model to actually predict that there is a letter here, it runs over these very many tiles independently, so it has no memory of what it has seen before. And then when it, you know, has predicted that there is ink in all of these different spots, we get to see the letter. And this prevents the model from having any context about what is being seen, because on this very low scale, it is impossible for the model to know what the letters are. So we had sort of a good idea on how to get the letters. It was then October and the hunt for the grand prize. And the idea for our solution for the grand prize was perfecting this approach, which comes down to two questions. One, how do you get as much quality data as possible? What is the good data for the model? And two, how do you make the model to sort of juice out every last ounce of performance out of your data? How do you make the most out of the data that you will finally have? So between October and December, we did more than 15 of these iterative labeling or pseudo labeling rounds. And what we eventually found out after many tryouts of, you know, how do you label different labeling techniques, different quality of the labels that you're making, is that quality and the diversity of your labels often trumps quantity. What that means is the areas that the model is unsure about, where, for example, your human inference can make up the letter, but the model is still suffering. This is usually the gold stuff. This is usually, what pushes the model towards understanding ink signal better. But if you give the model a bunch more of the letters that it already predicts very, very well, there is no new information for the model. This is something it already knows. So that was how to get as much data as possible. Now was that how do you make the most out of the data? And this sort of came down to this new trend of today's AI. This is the sort of the architecture powering, ChatGPT, powering a lot of the vision models is this idea of transformers, which basically treats any sort of data as a sequence. So for our cubes, it treats it as a sequence of images. And we use this special kind of transformer called timesformer, which is a very clever transformer that knows how to deal with 3D data efficiently. And this timesformer makes it uses the most amount of information from the data without, exhausting your resources heavily. And it is like a much bigger, a much stronger model than the first lattice model, but it was able to understand ink much, much better than these models. So finally, these are the links if you would like to take a look at the labels or the approach and my contact details. Yeah, thank you for listening.
See if they have any questions.
Yeah.
If you have any questions.
Yeah, because on the self-supervised learning, I'm using the self-level that contrasted OM. And so being able to self-supervise on this within 2D patches, yes, is it 2D image or 3D cube?
It's a 3D cube. So you give the model like a 3D cube, and then you apply some augmentation on the 3D cube, and this is like the other view that the model gets.
So it's different from the original.
Yeah, but most of the contrastive, it usually works on 2D images, but this special method is called VicReg, and they were arguing in their paper that this is something you can use on even different forms of data, not just images, but audio data or possibly text. So whatever you have, you can define different views or different alternatives of the data. You can basically use this method for.
Also.
Yeah, thank you.
I guess in the top, what is the biggest unsolved challenge right now with ink detections for the work on?
So the biggest challenge right now with ink is that ink comes in many different forms and in different scrolls, and this is kind of like why we haven't found ink yet in the other scrolls, but we sort of have a good idea on how to hunt down this ink. But it does remain a challenge that there is variation between the different scrolls. If you look at the ink from the fragments to the scroll that we have read, the ink looks different in there. We don't know exactly how many variations are there. So our best hope is to sort of make our methods as general as possible, but this is sort of the main challenge, yeah.
Do you have any idea why the variation happens? Is there different handwriting? Is there different conditions of levels of preservation?
I think so. Probably someone else would have a better answer than this, but I believe there's one factor known, for example, of the concentration of metal in the ink, and there is like quite some variation. That the scrolls have been under different circumstances, even in the same library. Yeah.
Great. Go on. Afro like that. Up.
Do you believe that? Do you have a question?
No, I was.
Yeah, he's just any ads.
Oh, I mean that.
It might also be that the fragments
underwent. I think all the fragments from jobs were on an oscillate method, which they were so big. I was chooses up that fact, so yeah, as impact disable changed in that. Hard to say.
question, Matt?
Yeah, what AI system are you using? I apologize.
We already met.
Yeah, so this is like an image segmentation model, specifically like a timesformer. So we used like a different sort of image segmentation models throughout the competition. Our first letters was an Inception 3D, which is a 3D image unit, and our final grand prize model was timesformer. So it's a transformer for 3D data.
Appreciate it. Thank you.
Yeah. Yeah. Any more questions? Yeah.
Thank you for a fascinating talk that's so clearly laid out. Sorry, your processes for bringing this up. But I'm just curious, you made it look so clear and simple, but how long did it take you to figure out that this was actually how it was going to work? How long did you spend chasing for false leads, red herrings?
Yeah, there were so many ups and downs throughout the journey of the competition. There were also so many different knobs to turn and to try out. I think in the end, the ink detection alone had more than 3,000 experiments run. And it was, yeah, maybe for me, it was from the end of July to December. It was, yeah, 14 hours a day, almost 7 days a week. Yeah.
I have a math question. So, in an earlier talk, they talked about that part of it was to change the tile shape from the cube to the between sets again. Is that a non-return or loose space?
Yeah, this was definitely one of the knobs that we played around with. The width of this tile was one factor, and how deep do you go? The main so one, for example, thing that that I experimented with was if you go too deep into if you include more and more depth, you start seeing different layers from the spiral basically, and if you don't do enough, you might miss the letter because you don't know where it exactly is in the segmentation. So this was one of the things that took some experimentation. Eventually, like, we settled on like a depth that is big enough to sort of have the full sheet, small enough to hopefully not have the other sheets, but still includes the other sheets. What happens when you have like a very large depth is the model maybe starts seeing letters from different areas and it doesn't know which one do you want. Like, there's ink here, there's ink in a different place there, and it's unsure which one it should give you. So this is probably why, for example, like tiles with very large depth, or even like large rectangles in the depth, suffer from this problem.
I have a question.
Yeah.
Mind if I ask you a question?
Yeah, of course.
From what I understood from your talk, you first saw letters on that segment from inside the scroll, having trained on an open fragment.
Yes.
Is that right?
Yes.
How did that make you feel?
I remember I was super excited for 3 days. I wasn't able to sit down. I would just run an experiment and then just circle around the house. It was very hard to believe, and I think I took a lot of time to convince myself because of previous ups and downs. So I was trying to be sure that it's not my aspirations that I'm seeing, but it's actually ink. But it was incredibly exciting. Thank you.